Well, good morning, everyone. Thank you for joining us this morning. I hope everyone's feeling good. I saw quite a few partiers out in the town last night, so expect there was a run for the aspirin and Advil this morning. My name is Mike Bernhardt. I'm with the Exascale Report, and I'd like to welcome you to what I believe is going to be a very interesting discussion on a topic that I feel very strongly about, exascaling your apps. We've got a very distinguished panel here today, and I'd like to thank you, gentlemen, first of all, for taking the time to join us. And we'll get into panel introductions in just a little while. First, I'd like to kind of set the stage for why we're doing this and why we think that this particular topic is important. We've been publishing at the Exascale Report for the past 18 months. And even today, I still think it's rather early for technical discussions, deep technical discussions related to exascale. Because quite honestly, there's just too many questions for which we don't have the answers. But has there been some progress made, and are we starting to lay the foundation for getting there? Absolutely, and I don't think anyone can deny that. As a member of the media, I'm as guilty as anyone of trying to go out there and push the funding agencies and push the powers to be to move faster, to articulate more for us what's happening. And I think that that's started to open up. I think the flow of information has really started to make a difference. There's been a lot of initiatives over the last 18 months that we've monitored and we've written about. Some of them have produced some wonderful results, and some have been more an experiment that just hasn't gone anywhere. But isn't that the nature of our community? I mean, this is primarily an HPC community when you look at how exascale is going to happen. And the nature of that community has been that we have to go down multiple paths. We have to try different approaches. And we have to try these different models. And there has to be some discussion as well as argument about how to get there. So the gentlemen that we have on the panel today, I think, represent a great cross-section of both the vendor or manufacturing side, if you will, the academic side, the end-user perspective, pulling that all together from their various perspectives, have, I think, rather keen insight as to not just where we are, but the kind of things that we need to do to move forward effectively. Now, historically, for the high end of the computing industry, I believe it's been rather a dull but true statement to say that hardware has always exceeded software by many, many miles, if you will. And I believe that what we'll find in this discussion is we have the opportunity to change that maybe for the first time in a major technology transition. And if we do this right, the results will be phenomenal for all of us. So what I want to talk to you just quickly about is the fact that we keep referring to a race to exascale. Now, when we first started writing about exascale on a regular basis, people would say, it's not about a race. And, well, yeah, there's international competition, but there's also international collaboration. And we're going to do more effectively if we collaborate than if we compete. So it's not really a race. And it doesn't matter who gets there first. Anyone want to say hogwash to that? It does matter. It does matter. There's a lot, not just to the bragging rights, but there's a lot of it's coming down to national pride. It's coming down to technology leadership as to how we're going to get there and so forth. So there is, in fact, what I refer to as a race to exascale. Now, what's more important, though, than the race and who actually wins the race, if the race is measured by whatever, the first running machine, is that we achieve practical and what I call beyond stunt machine exascale class systems. Who knows today what it's going to look like 6, 8, 10, 12 years from now as to what those first actual monstrosities will be. I'm sure they'll be beautiful and elegant, but they're going to be big. So that's one thing. But what will we do with them? How will we use them? How will they actually make a difference to all of us on this planet? So getting to the point of having usable applications, real good, practical, usable systems, is a major challenge. And our discussion is about it's not too late to start. We haven't already missed the boat. But it's also about, it's time to start. It's time to get serious about how we figure out what we're going to do with these applications to have them ready for exascale class systems. If we're going to do this right, we need three things. We need infrastructure. We need a healthy ecosystem from the smallest component suppliers up to the application developers. And we need those applications that scale. And that is the purpose of this panel today. So before we move any further, let me remind everyone to turn off or set your phones to vibrate, please. We would really appreciate that. We will have an open mic Q&A session after we get through some of our own questions, and we'll encourage as much interaction from the audience as you would like to share with us. So at this point, I'm going to ask the individual panel participants to introduce themselves briefly, tell you a little bit about what they do, and why they're concerned about the process of exascaling your apps. Satoshi, if you wouldn't mind, would like to start with your introduction.
How many minutes do I have?
Take as long as you want. 2?
You asked for it. The mic is not turning on. It's on? Okay. So my name is Satoshi Matsuoka, and despite my apparent American accent, I have a Japanese passport, and I don't have an American passport. I wear several hats, one of which is I'm the perpetrator of this machine called Tsubame 2, which some of you may have heard about, which probably has the record in terms of the fastest GPU-enabled being able to run the fastest GPU-enabled application at this time of day, which is about 2 petaflop, which won the Gordon Bell Prize last year and was subject to a brief introduction. Jensen's keynote was a dendrite solidification problem. But also I'm a researcher, I'm a professor, and my job is to work with very bright application people, and also with my team and also companies like NVIDIA and people like Jeff and my collaborators to try to enable exascale in some way. So I have been one of the core members of ISP, which is the international organization to try to identify problems, especially in terms of the system software, what are the problems, what we need to do, and in order to reach exascale. And finally, in Japan, we have started the effort towards exascale, and we have a white paper, which is a few hundred pages. So if you can read Japanese, you're very welcome to read it.
Okay. Or if you trust Google Translate to translate a 300-page technical document.
Yeah.
Well, you could do that too. You may need an exascale machine to do it correctly, though.
There you go. Thank you, Satoshi. Let's go to Jeff Vetter down on the end of the table there.
Well, good morning, everyone. I'm Jeffrey Vetter. I have 2 hats. The first one is at Oak Ridge National Lab. I'm the group leader for the Future Technologies Group, and there we look at new technologies. We've been looking at GPUs for on the order of 7 years now, and including porting applications like S3D, which you may have heard about yesterday, to GPUs. The other hat I wear is a bit different. It is at Georgia Tech. I'm a professor where I teach classes and have just finished a class of 50 graduate students and had all of them programming in CUDA by the end of the class. But I also manage the NSF project called Keeneland that's bringing GPUs to NSF, and later this year it'll be the production resource for GPUs across the National Science Foundation. That's a more interesting job in terms of, I think, the questions we're posing here, because what we've found is there's some really heroic efforts that have went on up till now to get applications up and running on GPUs. The real question is moving to that larger majority of users that can start porting their applications to GPUs. And based on some of the recent developments with OpenACC and the hardware support in Kepler and some of these changes, we think it's going to be a lot easier to make it useful for applications that didn't initially think they could run on a GPU. And so, as the book named Crossing the Chasm says, I think those things are going to be very important. So I'll finish.
It's awesome. So you're helping bring in the next generation of our HPC architects.
There. Well, let's hope so.
It's awesome. Thank you, Jeff. Olav, let's go to you next.
Yes, so good morning. I'm with Schlumberger, and my name is Olav Lindtjorn. So currently I'm outlining the future direction of HPC within our company. I spent the last couple of years here on the West Coast as a visiting scholar at Stanford, looking at the intersection of hardware architecture and algorithmic development. And prior to that, I have had quite a long time in R&D engineering management, managing the largest, most expensive applications that we have in terms of cycle consumption, as well as some of the most data-intensive acquisition systems that we use in our services. So from a HPC point of view, like what type of scale do we operate at? So I think we have a relative good size of installation. So for instance, in our Houston data center, we run something around 15,000 GPUs. So it should be one of the larger installations, I think. And we have multiple centers not of that size around the world. So we depend heavily on computation, and we depend on or expect to achieve significant progress the next couple of years.
For those not familiar with Schlumberger, could you just tell them briefly what your primary business mission is?
Yeah, so Schlumberger is a oil field service company. So basically what we do in terms that are related to this forum here is we do a lot of measurement, both geophysical measurement, surface measurement, in order to create a model or image of the underground. And we do a lot of model building for a reservoir when we have discovered a certain type of potential hydrocarbon reservoir. So we do simulation through porous rocks. And we also do a lot of what is called petrophysical measurements downhole after you have drilled and while you drill. And there is quite a lot of computation associated with that as well. But the dominant part is the geophysics processing.
Thank you. And Steve Scott.
Thanks. I'm Steve Scott. I'm the Chief Technology Officer for the Tesla business unit within NVIDIA. So I'm responsible and spend my time trying to shape the Tesla roadmap, figure out how we will go forward with GPU computing. I spent about 20 years of my career prior to joining NVIDIA last August at Cray, where I was CTO of Cray for the past 6 years or so. And as such, I've spent a lot of my time thinking about first, how do we get to a petaflop computer, and now how do we get to an exaflop computer? Many cycles thinking about this problem. We became convinced at Cray over the past few years that the only viable path going forward was to switch to a new architectural direction because of the growing power constraints. There's been a dramatic transformation in the IC technology that is making scaling currently and going forward much different than scaling in the past. And the inevitable conclusion was that we had to move to a different architecture, a hybrid architecture that used much more efficient processors, because the underlying IC technology was not going to get us where we needed to go. I spent a lot of time talking with people at AMD and people at Intel and people at NVIDIA over the past few years, and came to the conclusion that not only did NVIDIA have the most attractive technology, but they had a business model that worked, and it was pretty exciting. So that caused me to jump ship last August, and we're spending a lot of time now, as I said, understanding how to make GPU computing easier to use, more broadly applicable, and making projections out to the exascale. And there are some pretty big implications for the software that will run on these machines, and I'm sure we'll get into it in a lot more depth during the course of the next hour or so.
All right. Thank you, Steve. So that's your panel for today, and let's get them started and put them to work. So the first question I have for the panel is, and I made a statement earlier about, historically in the HPC community, We've been wonderful about getting these larger systems, next generations, new technologies, new computing paradigms out to market, but have also historically been very slow, lagged behind in bringing practical, usable software, especially when it comes to the applications. Are you concerned that this will be the case as we move closer and closer to the timeline of exascale? And I'll throw that one out to any of you who would like to respond.
Well, I think it's true that hardware gets most of the limelight, and we tend to talk about hardware. But if you look at how we actually spend our money, we do spend an incredible amount of money on software. Most computer, vendors spend more on software than they do on hardware. I'm not worried about the system software. I am a little bit worried about the application software. I'm not concerned that we're going to get to an exascale and not have applications. We will certainly have applications, but if you look over time, the set of applications as we go forward is getting smaller and smaller that can effectively use the largest machines. So if we want to have a broad impact, there needs to be a bit of a wake-up call and more people doing the work that there are, a smaller set of people doing today.
The rest of you agree with that?
Yes, I think if we look in our domain, the high end has always been dominated by geophysical algorithm, and I think we have always considered hardware as an enabler and been waiting for hardware. We have had algorithm that could use more cycles almost all the time of digital geophysics. And I think we know pretty much the algorithmic roadmap ahead of us. So I think we are ready from an application point of view to really step up in the time scale that we are talking about. So I'm not afraid that we will not have applications that we could run on these type of machines. And what makes it maybe easier for us is that we know that the main applications we have are very, they are, what we are in need of is more a capacity machine than a capability machine. So we know we can parallelize it. It's hundreds of thousands of experiments that can be run in parallel. So we think if the hardware vendors deliver, we will be there.
So Satoshi, let me ask you, so what Olav just described, as his organization goes, they're focused in a set of applications, and they're already looking at how to get those scaled to exascale. But if we bring these systems to market and only have one or two sets of applications, aren't we getting ourselves into a situation where we've got these machines and no practical use for beyond that few?
Yeah, so even at petascale, the effort for us has been to not only demonstrate, but to have real, truly useful applications, for example, running on our machine, and to the extent efficiently that it would use capabilities of the machine already available. Like on Tsubame 2, we have more than 10 petascale applications. Now, in the Japanese studies that we have been doing is to really work with the application community running for the K machine, and also for Tsubame and other machines to really identify, firstly, of course, identify the application needs for exascale. And certainly people do identify the needs in their respective domains, anywhere from life sciences to manufacturing to environmental science and to disaster prevention and energy. There have been strong desires from the application community to scale their code because of scientific needs. So that's a positive side. The negative side is when you really look at the challenges ahead with respect to porting these applications over to machines in the exascale regime, the machines, the way we scaled up to petascale has started getting to be a little challenging because of the transition to many core and heterogeneous architectures, and because of the physical characteristics of the machines. As we progress to exascale, it'll become increasingly more difficult. So the other process we really need to establish is to really do the code design process, where the needs of the applications are reflected in the architecture. So what we are doing is to start for the past 12 months, and now we have a more detailed project now, to really look at what the needs, what the parameters of the applications are. What are the algorithms? What are the natures of the algorithms? What are the requirements? What are the performance models? That really affect the architectures to the extent that we will have a variety of applications running on the machine. So it's not a trivial task. Really, co-design would be the big key.
Okay.
Jeff? Sure. So I'll jump in. So DOE started co-design centers about a year and a half ago, and they funded 3 initial centers. And just to describe it a little bit more detail, right now there are 3. There's the Combustion Center, the Materials Center, and the I'm having a moment here. I can't remember.
And the third center.
These are nuclear reactors. I'm sorry.
It's not
it's too early in the morning here, and the jet lag and everything's catching up with me.
It's okay, Governor.
Yeah. I'm not the governor of Texas now. So they've created those specifically for this purpose, and that's really encouraging because in the past, applications teams have been basically tossed new architectures and say, go figure out how to use them, and that's probably being dramatic, but there weren't additional funds set aside for them to go explore new architectures and new programming models. They basically had to do it as a sideshow and on their own time. This is an opportunity for them to go do that as a primary job that they have to do. And so one of the main things that we're trying to do is interact with the vendors, track the technologies and the programming models and the challenges, and tell the users what these opportunities might be. For example, smaller memory capacity is one that's come up. The first time we told them they might be 10 petabytes in an exascale system, they had a meltdown, literally. And so we went back and revised our numbers and are trying to figure out if there are options for things like NVRAM or some of these other technologies that might be possible in a system that would relieve that constraint. Meanwhile, we're trying to understand if the applications would actually be able to make use of that technology. And that's an example of this loop where it's really important to interact with them now.
Mm-hmm. Okay. Now, you probably can't answer this, Jeff, I'm guessing, to too much detail, but right now the largest system at Oak Ridge is Titan? Yes?
Yes.
Okay, and what's the size of it, or what do you expect it to be by year end?
Well, so that's a good question. It depends on what budget comes in. There's a number that's been published from 10 to 20 petaflops, and since it's a scalable system, there'll be a number of Keplers added to the system, and it'll be somewhere in that range.
And is it even feasible to think that Titan, through a process of evolving components and so forth and building it out, will become the exascale system, or not?
Yeah, with the mechanical no. With the mechanical infrastructure and all of those things, we've done some amazing. I pause because we've done some amazing things. If you look at the XT series that we've had at Oak Ridge, it's been almost continuously upgraded over the past 5 years to newer components. But exascale is just too much.
So that brings us to the. So how does your organization, how does your team start to think about what you're going to do to scale applications to exascale when you don't even know what the target machine will be?
Well, so we start exploring some point designs now, and then some of the things we're doing is trying to create benchmarks that represent algorithms they think they're going to use 5 years from now. Now this gets into a really uncertain area because they're trying to understand what algorithms they might use in that time frame. Meanwhile, we're telling them what hardware targets they're going to have to aim for in that time frame. And so there's an interplay there. The second thing is performance modeling and being able to do simulation and then even back of the envelope performance modeling to come up with things like working set sizes and floating point rates and number of messages that are communicated, and being able to at least give them a feel for what rates look in terms of a big O notation for performance models in that time frame.
Okay.
And the vendors have a pretty decent idea you squint a little bit, we've got a good idea of what these machines will look like in 2018, so we can project forward. And the co-design stuff is really key.
Yeah.
We've got a big group of people at NVIDIA that are computational scientists and mathematicians whose day in, day out job is to sit with the people that have the problems, understand the problems, not just the current applications, but understand the problems at a pretty deep level, and try to make that connection between the teams out at labs and universities that are doing the software development and industry, and in our future machines. And there's a lot of iteration back and forth.
So let me ask you, Steve. So I was with Intel in the late 90s. We did the road to teraflops, right? And that whole thing of getting to teraflops just didn't seem that difficult. Now, what's so different this time as we go from peta to exa? What really has changed? What's really so different?
The real difference has to do with this technology change that I mentioned earlier. If we look at the transitions from megaflop to gigaflop to teraflop to almost to petaflop, the technology was improving at such a rapid rate with voltage scaling that the number of processors scaled more slowly than the performance, because we were getting more processors, but they were getting faster. We've now gotten to the point where we're power constrained, and we have to unwind all of that we did in the past. And going forward, the processors have to get slower. They have to get simpler. So going from a petaflop to an exaflop, instead of only needing 100 times more processors, each of the last generations has needed only about 100 times more processors. We'll need more than 1,000 times more cores or threads.
Right.
And so it's that increase in the rate of scaling. It's not a night and day thing. I mean, there's nothing magical about an exaflop. We'll build a 600 petaflop machine first, and we'll build a 2 exaflop machine afterwards. But if we look in these generational terms, this next one is going to require a much greater increase in concurrency than any of the previous ones did, and we're already stressing the applications to find enough parallelism. It's going to require us to move to hybrid architectures, and it's going to require us, because of the power constraints, to start worrying about locality in a way. We can't just say, oh great, they're caches, locality is done. We're going to have to worry about hierarchical parallelism to extract all the concurrency, and we're going to have to worry a lot about the locality within a node. New levels of the memory hierarchy being instituted into the node, explicit data movement and management. So there's a lot of complexity and extra concurrency demands that are showing up now that we haven't really had to deal with in the past.
As to go a little bit more detail, everything has to do with the root of the problem is we're not scaling as fast, the transistors themselves, and because of the power constraints. And the power constraints have propagational effect. When you think of, because of the power constraints, we are forced to move to slower and many more cores. But when you think of and some of the reports have articulated that we need up to 100 million to billion cores. Now, when you think of billion cores, that's just a word, right? Billion is just a word. But when you try to estimate what the scale of this is, well, Tsubame 2 currently, if you count the number of cores in terms of instruction streams, not the CUDA cores, but like SMs and Intel cores, we have about 100,000. And now, this particular phone here has 2 cores. A billion core. How many of these smartphones do you know how many smartphones sold in a year last year? Can anybody guess?
A few hundred million.
300 million, yes. You've seen the slide before, yes. 300 million.
Yeah.
So that means each of these cores in this phone is weaker than the cores in Tsubame 2, certainly weaker than SM of Tesla, certainly weaker than the Intel cores. But we need, even if you assemble every one of these, we still won't reach a billion, the world entire production. So that's one example of a parameter. Now, what happens when we go to such a massive scale? Well, we run into many problems like programming and also scaling, because if you know Amdahl's law, the scaling will become extremely difficult due to the fact that there will be some portion of the program which will not be subject to speed up by parallelism. And this will become more and more evident. There will be time step problems. As we increase the resolution, the time steps become smaller and smaller. And like if you have a finite difference type of solver, not only you increase the resolution, you have to increase the time step, which means that you have to run the programs much longer if you increase the resolution, which will require more flops. So there's a more quadratic increase will actually result in a cubic increase in computational requirements. There will be less, as Steve said, there will be tremendous problems with data locality. The hierarchies will be very deep. We might be using non-volatile memory technology. We may have to go to a new programming paradigm where we will not be moving data as much. And all of these, well, with all of these parameters, they're just very difficult for programmers to cope with everything. So we may have to automate lots of things, including power constraints and moving of data and all those, which leads to an entirely new type of system software. So the challenges are quite astounding. The implications of low power is much more than what people usually would imagine to be a problem. It's not just simple scaling. It is an issue where the software really has to cope with these new types of architectures.
Okay. Let's have some fun. Let's take a question, and we're going to start with Olav and run down the panel here. Recently in the press, not recently, going back as far as the last ISC conference, at least one company made the statement that we will get to exascale by the end of the decade, and we will have all the applications running today running on exascale without the need for any new programming. Agree? Disagree? And why?
So I think if it is with the existing applications, so the benefit that we have is that as the capacity, computational capability increases, we are increasing or changing our algorithm. So I think we have enough of methods that we would like to deploy that need this type of level of computation. So we have almost a continuation of renewal of our algorithm. So, but even with today's algorithm, we can go to, as I said, we do thousands of experiments that can be distributed to more nodes. So it's an issue of. Pardon?
You're cheating.
Yeah. So it's an issue of distributing the data. So of course that is a challenge, as has been discussed here. But in terms of core algorithm, we don't need that level of capability of. We have a very nice application, but we have other domains where we are struggling even today, so we cannot scale today. So of course those type of method will even have a harder time to scale with the technology of tomorrow. So it's a serious issue, but for the maybe only domain where we are targeting exascale type of machines, I think we can really go to that level.
Wow. Okay. Steve, need me to repeat the question?
Yeah, no. So what Olav is talking about is important too. Running lots and lots of petaflop applications instead of one exaflop. I mean, if you get to an exaflop computer, that means you're going to have a much more cost-effective way to run lots of petaflops. But we do want capability problems to scale up to an exaflop because there are science problems that require that level of performance. So we've got to get there. Do I think we'll get to an exaflop by the end of the decade? Yes, I think we will. It'll be pretty expensive, but I think it's doable. Will all the existing applications run on that machine? Yes, absolutely. Unchanged, they will run on the machine. Will they run well? Absolutely not. So in fact, I think if you took even the most scalable applications today and just left it alone and tried to come back in 8 years and run it, it will run very, very poorly because of the huge increase in concurrency and all the issues that Matsuoka-san and I were just talking about. So. There's going to need to be a tremendous amount of work, and unfortunately the set of applications that run well will probably be somewhat smaller, but that's all of our job to make that set as big as possible.
Fair enough.
Well, yeah, so I wouldn't be echoing what my colleagues have said and agreeing with all of them, all the statements. But when you step back, it's all about what kind of science you want to achieve and what are the results. So it's a tricky business because the reason why you have differences in these numerical algorithms is not just because you want to run these applications more efficiently in terms of the better utilization of the resources machine, but rather it's time to solution. So time to solution, depending on what kind of algorithms you use, what seems to be less efficient in terms of the machine usage may lead to faster time to solution. Very typical is when you have, like, take climate type of application. It's still not, so people have been switching from some more indirect spectral type of methods to direct, finding difference direct solvers. However, when these are starting to run into their own problems, because if you know these numerics, you get all these boundary condition problems and resolution problems. You need very, very fine resolution. So, and then when you look at when you go back and revisit some of these indirect implicit solvers, they may not run as well efficiently on exascale. However, they may be more efficient because they don't run into these problems. But you still need to have very fast networks. So so things are not very clear whether the applications themselves will run efficiently, whether these but on these large machines, but it really boils down to how exascale machines of tomorrow will be able to run these applications to the scale where time to solution gets to be much quicker than today. Not how efficient they run.
Okay. Jeff?
Sure. Just to follow up, I endorse this approach of having the current applications running on the exascale system. It's going to have to run MPI plus X, and we're going to have to at least be able to run our applications there. Whether they're efficient or not is a different question. And this is where, if you look at something like the HPC Challenge benchmarks that came out of the HPCS program, they had a baseline model for all of their benchmarks, and they had an optimized version. And one of the reasons that we did that was so that you would be able to see what the cost was of not doing anything to your application. If you just take the MPI app and run it there, you get a certain performance. But if you invest some energy and time in optimizing it, you may get a lot better performance. And in fact, on some of the applications like random access and some of the others, you could see pretty significant performance improvements by using a different programming model or by using some optimization that was more than just a compiler flag, for example. And so, I think this incremental pathway to exploit those new technologies is what's going to make it easier for users to use an exascale system.
Yeah. Let's start with you and work our way back down the panel with one more question, and then we'll open it up to the audience.
Okay.
So, new programming models. Do we need new programming models, new architectures, and what might that look like?
Now, which
which is more important? Or is it a chicken and egg?
Yeah. So I think that the technology. So the programming model is very important to the user community. I mean, that's the power costs are the technology concerns, and that's where the architectures are going to be forced to do something different. This is where, when you start talking about things like disruptive technologies, applications users really, in some cases, have their hands tied. Because if you have a new programming model that conflicts with MPI, for example. Take a global address space programming model like Chapel or something like Charm++ that has this virtualization and a significant runtime. You have to rewrite your whole application. And there's, in some cases, no guarantee that you're going to get better performance than you have with your current implementation. And so, you have to be able to have some stability in that programming model so the user community can preserve their investment. Now, the one thing we haven't talked about is resiliency, and I think this is where programming models might matter more than people anticipate, in being able to hide failures and recover from failures and move tasks around for load balancing and preempt errors and things like that. But
these are the things we need to be looking at today.
Yes, absolutely. Sure.
Satoshi?
Well, when you talk about things like programming models and execution models, there are tiers. tiers in terms of the where they sit in the overall system stack. So when you talk about lower level programming model or execution model, obviously we have to go to much more asynchronous execution model, just as the GPU is already that. In order to cope with strong scaling, or and in order to do that, either you have to hide the latency or have a very shorten the latency to some respects, and asynchrony helps there. And people like Thomas Sterling has been advocating this for some time. Though the old data flow camp, if you remember, it's not a new idea. It goes back 30 years ago. So finally come to realization. So asynchrony, having more asynchrony at the bottom is really important. Now, having said that, do we expose that to the normal programmer? My opinion is not really. And there are two, but when you consider the programs to be for Exascale, there are two very distinct, I believe there are two distinct requirements. One is taking, the existing, not existing, not just, of course you may have to modify them, but taking the existing apps and their methodologies and being able to port them over. So there you will be using preserving investments, using familiar coding techniques, or maybe augmented with things like a single address space with PGAS languages, and be able to scale. So a lot will have to do with optimizing compilers, like my friend sitting in front of here, and runtime, and all those tricks, including resilience and power, all those tricks that the system software can play in order to allow people to port their existing code over and preserve the investment. The other avenue is to really have them programming at much higher level. Although they will be moving to a new sort of programming paradigm, these programming paradigms will be will take much less effort because they will be more tailored. Like DSL, there will be a domain-specific language which will be much more tailored to their particular domain. So that's again a low investment because they can code very easily. And then again, it's up to the compilers and the runtime to automate the process of optimizing to the architecture. So we'll probably see both of those. Existing, how do we move the existing programs and algorithms and codes over? The other would be simplified process, being more domain specific, using auto generation techniques.
Okay, good. Steve?
So I predict that on the first exaflop machine, the majority of codes will be MPI plus X, where X is some way of expressing on-node parallelism. Flat models are out. The idea that you have a flat MPI programming model and that will scale to an exaflop, I think, is pretty, very unrealistic for all but the very, very simplest of codes. What is the plus X? I think we're likely to evolve to a directive-based model, something not too dissimilar from where we are with OpenMP today. There's the new standard for hybrid directive-based programming, OpenACC, which is just getting off the ground now with the first implementations from PGI and CAPS. I think that Intel, if they ever ship Mike, will end up doing something very similar with some sort of a directive-based approach. So I think that is likely to somewhat converge. We're going to have to find ways of augmenting straight MPI to not worry just about parallelism, but worry about locality and resiliency, and which have both been mentioned here. So some ways of expressing locality, we're going to have to deal with this deep memory hierarchy. So we're going to have to augment these programming models. I don't think that we're going to ask users to micromanage all the details of on-node parallelism and on-node locality. We're going to see increasing usage of auto-tuners as the nodes get more complex, and it's really up to the compiler and the runtime and the auto-tuners to do all of the knob twisting. But we're going to have to find ways to express the locality and express the parallelism concurrency in a neutral way that can port across architectures. There'll be other applications that need something entirely different than MPI. So I'm a big believer in global address spaces. The ability to get much more fine-grained communication with lower overhead. There are there are emerging markets like data analytics, graph analytics that are not going to be well served by MPI or MPI plus X, that need a global view or at least a PGAS style of machine and programming model. So yeah, there are going to be some ways that we branch off, but I think most of the code is going to be taking these sort of existing distributed memory apps and just augmenting them to help deal with locality and resiliency.
Okay, good. Olav.
Yes, I agree with a lot of what has been said, that for the majority of application this is true. But again, we have a set of applications that are more like an instrumentation, run like an instrumentation, where really throughput and performance and tweaking the most out of the hardware up to the last percentage is critical for it to be economical to run these type of services. And for those classes of application, I've always been amazed with actually how static the approach to the problem has been over a couple of order of magnitude increase in performance. So even without a lot of these nice tools and abstractions coming along, I think with the existing method, a deep knowledge of the architecture, a deep knowledge of the algorithm, that we will be able to achieve this level of performance. So we are a little bit skeptical to maybe the tool providers. So we are gambling that actually hard effort can lift this type of application that are more like a dedicated instrumentation to this level of performance.
Okay, awesome. Let's, anybody in the audience would like to ask any questions at this time? Michael?
Oh.
I can count on Mike.
Yeah.
Yes.
They knew that was coming.
I could go on, but
Have a seat.
Yes.
I could stand up there, right? So, given that exascale, the story I'm hearing, or at least the point I'm hearing is most of what we didn't learn much from tera to peta transition in terms of programming models. And we're going to have to restructure our codes as we move to exascale. Olav may be the skeptic in this point, but the rest of you seem to... What I heard was apps will have to be restructured as we move towards exascale to take full advantage of those systems. So, when we reach that level, what are the petascale systems going to look like? Are those restructured apps going to work well on whatever petascale systems we have? Are the petascale systems going to look like a small exascale system, or are they going to look like Titan? You see where I'm getting?
Yes.
You know, there's a lot more motivation to restructure your app if it's also going to work on the system you got in your closet.
We're reaching an unprecedented point in our history where at a high level, the right way to build a processor for this computer is the same as the right way to build a processor for a $100 million supercomputer. That has never been the case in the past, and it's because of this power constraint. You need to have lots of simple processors, and you scale up the number of processors versus the type of processor, because they all have to be designed for energy efficiency, and that's true in the phone, that's true in your small server, it's true in your supercomputer. So the node architecture, because of power constraints, is going to be pretty similar up and down the line. And so what do you have to do to make your code run well on an exascale machine? You need to expose concurrency and expose locality applicable at the single node level in a way that is relatively neutral and can be mapped onto different machines. And so if you do that successfully, that can be mapped onto a small scale, a petaflop machine, a teraflop machine on a single part of a chip, or an exaflop machine. So I think there'll be no incompatibility for apps scaling down.
So I'll be a little bit more skeptical. The thing you see now is a real diversity in the large-scale systems available to the user community. You have things like, traditional homogeneous systems. You've got K, you've got Blue Gene Q, you've got accelerator-based systems, and there are potentially apps that have to run across all of those platforms, take climate models or things like that that users have to use. Right now, there's not a single way to program all those. And to get the user community to move to that, there really has to be an investment in software so that they have more portability across those different platforms. And those are probably going to get more diverse going forward, at least for the next couple years, before they converge. And so this is the wrestling match we're in, trying to figure out what that programming model is, because it's all changing.
Well,
So
I'm in agreement with Scott because
I tried.
well, this transition has already started with the likes of Blue Gene, with this extreme mini core machines like Blue Gene and like Swami and K. K has 700,000 cores, so almost 1 million cores now, and there's just no way to even program that at that level without being able to expose parallelism to the extent that none of the legacy codes that that has strong scaling components would really work well on those machines. So, this transition has already started, and as we move forward, although we may have to make all these adjustments along the way, I believe that the transition to many core, in fact, as heterogeneous architectures to deal with a strong scaling component will persist. The flip side of the coin is, assuming you have an exascale system, do you have lots of applications running at petaflops or even smaller? Is there like a downscaling requirements? And I would say people have this very similar sets of requirements for applications running on these smaller petascale machines, even down to the consumer level, and they'll be uniform just precisely because what Scott had said, these machines will look very much the same. So I think we have a brighter future where if we can get the scaling problem solved some way, then these things, because of we can even run stuff on these cell phones, and actually a lot of the apps running on cell phones may require supercomputing power because it'll do something a lot different than what they're doing now. Not just browsing, they may be doing real-time recognition, they may have artificial intelligence and all that, which will require tremendous compute power.
Did you have another question?
I did. Seeing no... Scott, I think, brought up auto-tuning.
Yes.
Okay. So dealing with programming models, this is more a question actually for Olav and Satoshi, who are more in the apps end than the system end, I think, is to really take advantage of auto-tuning, where the system, the compiler, runtime, whatever, will try alternatives. Then the programming model, my supposition is, to enable that, you want the programming model to expose the alternatives to the system. So the programmer would say, here are some parameters that you should try, tiling parameters, or maybe here are alternative algorithms. You could do this kind of solver or that kind of solver. You choose, because depending on what particular architecture you're on, it may be different, or the scale you're running on. Is that a viable thing to expose to an application programmer?
It is certainly desirable. If it is doable is a question. I think there is some hope for a high-level abstraction, a domain-specific language combined with auto-tuning to be a great help for a lot of applications. If I believe we will achieve that in 3-4 years time frame is a different question. But certainly I think there have been some examples of domain-specific language that has been translated very efficiently to certain hardware where you give your parameters at a very high level. That is certainly very interesting.
Good. Well, firstly, let me state that auto-tuning is not a technology of the future. It is here now. On Tsubame 2, many apps use auto-tuning already because as I said, transition has already started happening, and because of the complexity, I call auto-tuning systematic hacking. Right. And
But is that auto-tuning in the app, or is it something on top of that?
yeah, so that's what I was going to get
right.
to. Yeah, so right now people usually do their customized create their own customized auto-tuners. There are work our collaborators are doing to design auto-tuning languages, for example, descriptions by which things like choice of algorithms, parameters, etc., can be encoded as pragma, just like OpenMP, annotation into the program, so alternatives can be designed. I think there are many approaches like that where the users or the programmers or the library builders will be able to expose the potential alternatives in a very standard format, such that these can be exploited. And so going from really customized to more generic type of auto-tuning will be a roadmap. Is something people are already working on, but certainly is a viable roadmap.
As a related subject, there are libraries now that are themselves adaptive.
Yeah.
Right. So you call an FFT library, and then based upon the size and aspect ratio and conditioning of your matrices, it does some runtime checking and then calls different algorithms, different plans for executing the FFT. And there are similar, cases in other areas.
But we want to enable auto-tuning.
Yes.
Right.
Use
Right. Not just by ninjas.
Right.
Because he's smart and he knows how to do it. I want to do it.
Audience questions? Anyone?
I work in more of a geophysical space, so I sort of relate to some of the comments here. I'm curious about the level to which there's been efforts in exploring functional parallelism, where you might have multiple physical processes happening and could be programmed instead of serially, where one thing happens after another. The degree to which that parallelism could be exploited as well would require new research to look at how you would integrate multiple processes happening at the same time and achieve perhaps a significant bump in scaling because you're allowing these processes with also knowledge that data locality needs to be preserved, that this could be done in such a way that it makes scientific sense and can be a way forward. And I wondered what your thoughts are on that.
Are you thinking more from a software perspective, or are you actually arguing for different types of heterogeneous hardware that's designed for certain types of functions?
So this is more in terms of the algorithm itself.
okay.
So the design of the algorithm might be that you've got now graduate students or others that are engaging in how do we develop the next generation of physical models that will allow for, have some flexibility in the way that physical processes are numerically managed and solved.
Is that the UQ question?
Interesting.
I don't have any particular insight in that, other than that falls into the general category of thinking very hard about the problem you're trying to solve, not your current algorithm, and how do you expose as much concurrency as possible. I mean, that is one example of doing so, where it's not in a data parallel way, but it's in a task parallel way. And so we can't throw anything out of our bag of tricks. Right. Just from an architectural perspective, we need to look at distributed memory parallelism and thread level parallelism and vector SIMD level parallelism, et cetera. From an algorithmic point of view, we need to be looking at different types of data level, instruction level, and task level concurrency, and that falls into that camp. And it's kind of an application specific thing.
Right.
I think what you're asking can be generalized in terms of this new buzzword called uncertainty quantification. Meaning, different types of numerical algorithms, when they scale, for example, would lead to different characteristics in terms of numerical stabilities and so forth. And there's a huge work on that, especially in the U.S. DOE was really concerned about, if we can run the code, but can we trust it? Can we trust the results? And that's a very interesting question because, as I said. As the problem's complexities, and not just in terms of their numerical complexities, but the algorithmic complexities as the machine scales become quite prevalent. A classic example is, do we have enough precisions in the floating point, and that's why we move from single to double. And now we are having people advocate for some type of apps. We need to go to quad precision type of computation, which actually with current architectures do not do very well. There are certain properties about direct solvers and implicit solvers, and in some cases, direct solvers may not be appropriate for very large-scale problems, and they may need to go to implicit solvers. Actually go back to implicit solvers. So it's a very interesting area. There's no off-the-shelf answer, and it's just that we have to look at the problem in the context of this extremely large machines, how numerical algorithms behave in that context.
Right. Yeah. So just to follow on that, I mean, at the highest level, if you look at the functional decomposition and as opposed to a data parallel, and you think about uncertainty quantification, things like climate models typically run many different simulations with slight tweaks or perturbations in the input set, and then they merge those features, those outputs at the end to get a kind of an average trajectory for the climate. Even at a higher level, you run multiple climate codes, even different types of codes that use different physics models and numerical models to represent those, and that gives you more confidence in your simulation, and that's where the UQ comes from. So I could see this not being a data parallel problem. It would be more of a functional decomposition. It'd be at high granularity, but it would kind of have many different characteristics as they're all being executed simultaneously. Is that something along the lines of what you're describing?
Yeah, when you look at a typical model, it has a series of steps within a time step. You have a series of processes that happen, and they happen often linearly, serially. Well, in the physical space, it doesn't work that way. And so if you could actually model closer to what is physically happening in the atmosphere, where all of these things are happening simultaneously, well, you have a beautiful scalable problem there if you can figure out how to handle and manage data locality and other elements in which you're going to be sharing this information across your compute space.
Yeah, and coupling those things together tends to be, the climate model in this way can run with multiple parts, like the ocean model and the sea ice model. They can run at the same time on the same system and then be coupled together at the end to exchange grid information and do nearest neighbor updates and things like that. But this idea of having complete physics packages running in parallel in the same time step is, I think that's entirely, in fact some codes are already doing something like that, where they have this functional decomposition at the OpenMP level, for example.
This is where a university community would be engaged in doing the research, the basic level research, to what degree can this be done. And this is an investment that you'd want to have happening now, such that when those architectures are available, you can show that there's algorithms that will scale in this way as well.
Sure.
Okay. Any other audience questions? Okay.
I guess after the discussion, I'm not left with a good idea of what the kind of ideal programming model is going to be for an exascale system, particularly in regards to actually managing the parallelism, and but there are many references to managing data locality. I was just wondering if any of you had examples of kind of current system programming models or languages that were kind of on the right track or in the direction or doing the right things that you think would get us to the management that you're thinking about.
Doing the right thing.
What's that?
Doing the right thing?
Yes. Well, it's an open area right now. I mean, I can name at least 5 different efforts that are looking at ways to represent hierarchical parallelism that's different than MPI plus OpenMP or OpenACC. I mean, there's the Charm++ work, there's Chapel, there's Legion at Stanford. There's several different of those programming models that will require a fundamental change in the way people program their apps, but there is some benefit to it because there is this automatic management of locality and hierarchical parallelism that takes the user out of that loop, so you don't have to worry if you have 3 levels of cache or 4 levels of cache. The system manages that for you. Other comments?
Well, in terms of expressing locality and how the data is laid out. I mean, there's been numbers of years of efforts in doing that, and with some, and we are seeing what we're seeing now, and the current efforts are sort of crystallizations of the failed efforts. For example, things like, do we remember HPF? Yes, high performance Fortran. Yeah, which for some reason never, well, kind of worked on the Earth simulator, by the way, but it's kind of gone. And we have friends who have actually spent the effort trying to do that. As I said, if we regard the two success models as being porting over existing applications to Peta and Exascale, we do see a fleet of languages that are trying to express locality in terms of various types of annotations in the program. Assisted perhaps by compilers, which may actually generate these types of annotations because compilers can also assist in people's to give additional information so that they can actually discover locality that people are not aware of. And so like Accelerator compiler that PGI has actually helps you do that to some extent. The DSL type of effort, I think, could also be very fruitful because it may express the locality in terms of the domain of the science rather than at a much lower level. So you're saying you have these, like you may have some physical phenomena, and you may be able to express these at a much higher level. But because you're expressing these at a much higher level at the problem level, the domain, the locality of the problem may express themselves more directly. So. And there are efforts like that. We have work like that too. So there are lots. I think there are lots of trials, and none has won out. But it's an evolution. It's not something that has suddenly cropped up. People have been working on this for many years, and we're seeing improved versions as time had progressed.
We're going to do one more question before we do our panel wrap up.
My question is more about when the systems become so very large, what do you do about the fault tolerance when either a node fails or some memory is going bad, and all this has to be done on the fly? You can't afford to restart your program.
Right.
Is there any thoughts about how to do that in some automatic fashion so that the user doesn't have to deal with this problem?
We used to have something called system initiated checkpoint restart, where every once in a while the system would checkpoint all the memory out to disk, and then if you had a failure, you could roll it back. That's transitioned to application-initiated checkpoint restart, which is much more efficient. The application can either do it itself or ask the system to do it at a time of low state. If you extrapolate out to the scale of systems and the reliability of the components, you'll see that that's not going to scale because the mean time to failure is getting shorter, and the time that it takes to checkpoint all of your system memory out to rotating storage is getting larger, and then when they get within a factor of 10, bad things happen. But if we move to using non-volatile memory, flash or something of that sort, so that we can do very fast checkpoints, then if you do the math, checkpoint restart will scale all the way up to exascale. We can do whole program rollback as long as we can do very fast checkpointing, and we'll be okay. The big problem is that there's silent data corruption. You don't necessarily catch the errors, and that's going to get worse as we push up, again, component count, and we push down into deep submicron lithography, and the components themselves get less reliable. And so we are undoubtedly going to have to move more toward application self-checking. applications will need to know whether or not they're resilient to failure. Some are, and you can just they'll still converge even if you throw an error into the mix. Some aren't, and they need to do some sort of self-checking to detect if there has been an error. This is something we obviously don't want to foist upon the chemists and physicists and climatologists and make them figure out. We have to create sort of frameworks that are easier for them to reason about and to take advantage of. But we're going to have to make the applications themselves aware of failures and more resilient. And then we're also doing research into making resiliency scale better by not having to roll back the entire application and being able to contain faults and then restart just part of an application. And that may also affect the users. So a lot of research going on in this area.
Right. Yeah, I would just add that this area of algorithm-based fault tolerance is a growing area. If you go to a lot of conferences lately, people are really looking at this, and the results are pretty amazing. Like Steve was saying, with the iterative algorithms, there some results out there right now that compute triply redundant calculations on things like the pointer math, but the general data set is not triply redundant, and even if you get silent data corruption, you might run for a couple extra iterations, but you converge anyway, and you get an answer that's within the bounds you're looking for. And that really shows a lot of promise, because remember, even with the GPUs we have today, you can turn ECC off, and it gives you a little bit higher performance, right? And so there may be some benefit to having a memory system that has these different classes of memory in it that you can, put things in based on how resilient they need to be.
Yeah. Well, agreeing with my colleagues, because actually we work on this subject. That's one of our primary subjects of research of resilience. There are a lot of techniques being developed at the system level. There was an SC paper last year in which we designed an algorithm that really exploits the local storage of the nodes of solid-state local storage in a very effective way to really substantially, by order of magnitude, decrease the checkpoint time while preserving the resilience in terms of multi-node failures. So they work like that, and the algorithm fault tolerance for sure. Again, the problem is how do we describe these? How do we not stress the users in not having them describe the resiliency aspect of their algorithms or programs to the extent that they will get tired of doing that, such that it becomes non-effective. So that's a real challenge. And again, one solution is to go to higher level descriptions, like DSLs, where these types of semantics of the application can be expressed naturally, such that the correctness criteria can be synthesized from the description of the domains themselves, rather than being low level. And of course, there are lots of other types of research going on where, like, libraries can be fault tolerant. It can have multiple executions to cope with silent errors. So we have so much flops. Why don't we just use the flops? Because we have excess flops. So why don't we compute twice or 3 times? And maybe we won't have as much overhead after all, because actually the real overhead is in memory reads and not the compute. So so there are lots of variety of work going on, lots of exciting stuff, but it's really I don't think we have a panacea yet. No, fault and resilience is a sort of a subject that's been studied for a long time, and but we're approaching the scale of system in an unprecedented fashion, such that there's no one single technique that's applicable to all. Yeah.
Yes, I agree with that. Resilience is maybe the biggest risk that we see in our domain as well. Maybe specifically outside of the geophysical domain, that we actually do not have any type of framework or methods actually to handle specifically silent error. In the seismic domain, we have had from time to time implement at the application level functionality to handle silent type of error. So I feel there we know maybe a little bit about the cost it would imply for our runtime code, but for many applications I think we have absolutely no clue on how to handle silent error if that really becomes a major issue.
Okay, so for the closing comments, I'd like to ask each of you to give the audience some brief advice. And let's start with you, Professor Vetter. You're talking to the next generation of folks coming along. You're talking to the new wave of application developers and programmers out there.
Wow.
What advice can we give them? What should they or could they be doing today to prepare for exascaling their apps?
Wow. I feel like I gave this speech a couple weeks ago when my class was wrapping up, right? You know, I think it's a great time to be a computer scientist, actually, because over the past 20 years, there was a time period there where things were really stable. Programming models didn't change a lot. Architectures were, as Steve described, pretty monotonous, just rising in clock speeds and instruction sets and all that stayed the same. Now there's a lot of exploration going on, and I think the key would be to just remain optimistic that we're going to get there and learn new programming models, experiment with new algorithms, try to figure out what's working, because I have no doubt the technology is going to get there, but it's really this question of applications and software stack that really needs to be addressed, and we need people exploring that.
Cool. Keep the faith.
Yes.
Well, my advice, if you are a computer scientist, talk to the application people. Well, don't listen to their solutions, listen to the problems, by the way. Particularly their solutions are wrong, but their problems are right. If you're an application person, talk to the computer scientists, because oftentimes they may have clever solutions that they've never had thought of, or there may be no solutions, so you stop working on the problem. I think we're at an era where myself being a trained computer scientist, I've been talking to application people in a very, very close fashion and in an unprecedented way. And I think it's because we have all these problems with all these machines as we go scale to exascale. But on the other hand, it's really enjoyable because it gives me new problems to solve. And I see happy faces of application people when they get their problems solved working with us, and they really get their performances and get their science done. So it's a great time. But go talk to your, not adversaries, but their your counterparts, because I think it's very fruitful as we go exascaling.
Steve?
I don't have a lot to add here. If you're, the question was, what advice would you give to application developers? And if you're an application developer that has the opportunity to engage in co-design, you happen to be at a large government lab or something, or a strategic university, absolutely do that. But just in general, if you're a scientist who's got some code that you're wanting to run well on systems 5 years, 8 years from now, don't be thinking about incrementally enhancing your parallelism. Step back and say, wow, what if I had to have 1,000 times more parallelism exposed than I have today? 1,000 times, if this is a machine off in the future, because I don't want to have to do this again next year. Do I have to fundamentally think about refactoring my algorithm? Do I have to fundamentally think about refactoring how I lay out my data to do that? Start thinking about practically infinite parallelism. Serial operation should be the exception rather than the rule. With that mindset, if you can structure your codes in a way that then gets expressed, we'll be able to take that code and with the compilers and runtimes map them onto machines with increasing levels of parallelism.
That's good. Olav.
Yeah, I agree with all of what has been said. So over the last couple of months, I have had several engagement with a large portfolio of products in our company. So it's a lot of software that is written across the business units. And so I have a pretty strong view on this, as you probably have already deducted. So I think the advice that I really would give is that in order to get performant code, you need to understand the cost function of the hardware. There is no way around it. And without having a minimum understanding of the algorithm, you will, and the ability to tweak the algorithm with the cost functions of the underlying hardware, you will not get a high-performant code. So my advice is that you should really get that knowledge both on the algorithmic side and the hardware structure side.
Awesome. Thank you very much. We have a few minutes if anyone wants to try to talk with these guys individually before they leave the room. Remember that there's a keynote at 11 o'clock in Hall 1, I believe it is. Yes, Hall 1. And please join me in thanking our panelists for their participation today.